Hola, hola, hola. You back. Yes, you back. And we back as well. You must be giving us a lot of confidence by keeping coming back. So here we are. Guess who's back? Guess who's back? Guess who's back? Yeah. Let's do this. We are doing the digital to analog converter using summing amplifiers, but there's another way. I said there's two ways. I'm going to come back and do another way. All right, but for now, we are going to, well, it's going to be using what call this, just a different way. This is the one way of doing it. There's another way, but still using summing amplifiers. So this is the one application for the summing amplifier, digital to analog converters. All right, now we're going to look at a specific type, the BCD to analog converters. Now let's remember what BCD is. Last time I chose these values carefully. Why? This is a theoretical scenario where I chose these values carefully because I wanted you to see these values will give us a scenario. This is an example of values. The other values that could do the same, but this is an example of values that you saw giving us what? Giving us what call this? What call? Where one where 111 will give us the 15 we know, and where probably 1001 will give us the 9 we know. So I chose those values. So in practice, sometimes we are given values that would give us different values that have somehow a relation to our ultimate value. Let's say, for instance, you could have 1111 giving us 7.5 volts, for instance. All right, the full voltage, with the full load voltage being 7.5 volts, the full load voltage being 5 volts. Therefore, that would mean that our 111, which is 15, is actually represented by the digital, what call it, the analog output that we've chosen. We can manipulate it to give us the value that we want in different ways. Look, this is this is engineering, so we can do a lot of things. We can amplify the output voltage, you can do whatever to the desired value if there's such a need. All right, but with these values that I've chosen, I've made sure that 1111, any combination will give us that value. We saw previously how 1111 gave us what call this, our 15, and we saw how 1101 gave us our 13. All right, so these are values that are chosen for that specific scenario to actually articulate the meaning, to give greater meaning, emphasis on why this works. All right, so let's go on and say, now I want to do, what do I do to this is, oh, by the way, I have taken liberty to indicate what was a general output here. This general output simply says, if I could have more than this, I've got 4 in this case. In our first example, we're 3. I have 4 in this case here. Let me remove this. I think in our previous example, you might have noticed that there was I4 here. Yeah, I think it's set from an example that we made, and we didn't delete the I4. Well, there's 3 of them there, so there can only be I1 to I3. Well, in this case here, there will be I1, I2, I3, I4, but there could be more. In this case here, there will be more. If there is more, like I said, general case, maybe let's say n, any number, then you'd add all those currents. Right? Remember, this is from Kirchhoff. All these currents coming to this joint will be added together to get the input current. Remember, the input current is whatever comes in here, which is going to be rejected by the op amp and sent through the feedback. So our I total is sent through the feedback resistor. Those are basics that we need to keep remembering. If we forget our basics, we can't handle the stuff in front there. We need to keep our basics intact. If our basics are, if we have a strong base, base like a foundation, our basics are like our foundations. If a house has a very weak foundation, it won't last. If a house has a extremely strong foundation, it will last the longest. All right, so let's make sure we stick to our basics. We don't forget our basics. Now let's take our scenario that we have here and say, all right, I want, how do I then have a factor of 10 here? How do I introduce? Because what I'm going to do now is I'm going to have BCD, meaning that if I've got 19 volts, how do I get 19 volts from this? I must have a BCD input of 1, 0. Oh, I said 19. I don't like 19. It's too simplistic. Let's have 79. Let's say we've got 79. Our input must give us 79. How do we do this? It means what we need to do here, we need to have what? We need to have 1 1 0, an input of 0 0 1 1 1, giving us, and 9 is what? 9 is 1 0 0 1. So we need to have an input like this, giving us an output that is more or less 79, 7,9. You know, we can play around with this. It can give us 7,9, but in our manipulation there, we can make it, we will know it means 79, right? So it depends on how you do things. So the one way, the obvious way would be, if I factor this, remember, the most significant bit is represented by the smaller resistor. All right, there's going to be more current there, therefore it's going to contribute a greater voltage. All right, there's going to be lesser current there because the resistance is too high. There's going to be lesser current there, therefore it's going to contribute a lesser current, therefore a lesser voltage. So the greater the what, if I want to increase my bits, my what call this, if I want to increase my let's say if you look at 7 and 9 here, these are units and these are tens. If I want to increase, and remember, I could have tens, I could have comma 3, which would be 0 0 1 1 in BCD, you know. So these comma tens, ne? So now if I want to increase by a factor of 10, I must actually decrease by a factor of 10 on the resistance. Why? If I want to go bigger, the smaller resistors give us bigger values. All right, so if I want to go bigger, if I want, for instance, to just let me put this, let me stop talking and show what I'm trying to do here. Let's say I clone this and I have a set down here. Let's say that I don't want it to clash with my other. Let's go and say this here, I want it to be a set, but I am going to reduce that factor there. Okay, I'm going to reduce that by a factor of 10. What does it mean? I'm going higher because a smaller resistor gives us bigger current. So if I now come and say, instead of 100k, I go down by a factor of 10, I divide by 10, that will be 10k. This here would have to be half, to be 10 less than that. This will have to be 5k, 2,5 k, and then this will have to be 1,25. Because when we close this to the same voltage, this will have a lesser resistance and it will give us a bigger current than that. So this will have a 10 times bigger current than this. So you can see the factor of 10 coming into play here. So now obviously we don't want to show it as two different sources like that. So what we'll do is we will remember always show dots to indicate that it's connected. Always show dots to say it's connected there. All right, not good practice, it's a must. It is not good practice, it's a must. Good practice is something that you may do and it's good. This is not good practice, it is a must do. If you don't do it, we'll simply tell you it's not connected and we'll refuse with our marks. Now let's go on and say, how do we then do this? Let's come and say, I want to have, for instance, I've grown up by 10. So let's say I want to have 79. This is going to have to be, this is the more significant. It's got the lesser resistance, so it's more significant. This is 0. The other one is 1, 1, 1. And that one there is the next set. Another, the next 4 will represent the next set. So this is 1, 0, 0, 1 for that D there. All right. So how does this work? Let's see if this works. So our V out is given by that. So let's work out our V out. Our V out is equal to, oh, there is a minus here. Why? It's an inverting format. It's an inverting format, so it's a minus. So there's a minus there. We shouldn't forget that minus because it's inverting. Now, what we then do, we then say everywhere where there is a 1, we are going to involve, because everything, that our part is going to be plus 0, plus 0. If the voltage is 0, if the switch is 0, it means that voltage there is going to be 0. It's not connected to the 5 volts, so that will be 0, 0. So everywhere there is 0, we're simply going to ignore. We're going to add only the ones that they have what? That they have ones. So let's come and say our V out is minus RF, which we know is 20k. Okay, into, Our voltage is the same all the time, is 555. When there's a switch there, the voltage is 555. Digital, okay, our digital input. Now we come and say that P there is what? That P there is 2,5K. So that will be V1, which is, in this case, it will be V2 because V1 was eliminated. So this will be 5 over 2,5. 2.5K plus that one there is 5 volt because it's one is closed. One means it's closed, so that will be 5 volts again over, but that there is 5K plus that one there is closed, so that's what? That's 10K, so that's 5 volts over 10K. But the next one is on the next set, so we continue. This is just a parallel set, not really parallel, but these are basically voltages that are being supplied to what? To, yeah, it is parallel because it's what this side and what that side. So they can all be added together. All right, the result will resolve itself. You don't have to worry about that. Now you're going to say this one is 12,5, so that will be 5 volt because once it's closed, it's a 5 volt over 12,5. Okay, I skipped the order. That one was 0. 12,5 kilo plus that one is 0, so 0 plus 0 plus that one there, which is 5 volt over 100K. 100K. So here what do we have? We have a scenario where, let's do a little bit of math here. Let's see if we need to do that. That K is common to all of them. I could have had the K is there. I could have said times 20K, times 20K. I would factor it in, so I can take out that K with all the K's here. I think those who are not too bad with our maths will understand what we're doing now. All right, so all we did was, this could have been in there, this could have been in there, so the K's are actually common, so between the denominators and the numerators, so we can eliminate the K's in this specific case. That there becomes, if you look now, this is 100. Everything there's going to be, I'm factoring in that 20 there. This is going to be 100, 100, 100, 100. So it means every fraction is 100 divided by something. So I'm going to say 100 divided by 2,5. 100 divided by 2,5 is already 40, right? 100 divided by 2,5, 100 divided by 2,5, and we have the 40. Yes, we expect it to be 40, and we are right. Okay, 40 plus that one there is 100 divided by 5, that's 20, obviously, plus 100 divided by, oh, this is all going to be negative, right? Let's not forget that, lest we forget. That one's going to be 100 divided by 10 is obviously 10, plus 100 divided by 12,5, that's obviously what? That's obviously 4, no, 8. Why 8? Because 25 would, is 4. I'm wrong, it's 4, not 8, 4. Why? 25 into 100 is 4. So 100 divided by 12,5 is 8. I was right. Alright, I don't know why I had 8 and then my mind sort of played games with me. Now then we have 100 divided by 100, which is 1. Alright, that's fine, yeah. This is 12,5, 25, then 25 into 100 is 4, so it's 2 times 4, which is 8. Alright, that's fine. So 100 divided by 100 is 1. So this here is what we have, and then what do we have? If we look at this, this is going to be, you can see these sets, the first 3 are all having zeros. They are in the tens. We are adding 4, 2, 1, but we are adding tens. You can see here we're adding units. So as you can see, this becomes minus, this is 60, 70. Yes, 70. And then you see that one is 9. And we got exactly what we wanted. In practice, we don't do that. We can have it as other numbers here that can still be interpreted. But let's not mess up our things right now. Let's just relax and say we have 79 volts for that one. All right, you can see how we've translated our BCD 79 into that. How do we put the 10th? I said if we want to increase by a factor of 10, we increase our resistors by what? By a factor of 10. We increase that by a factor of 10. All right. Now these are units. These are tens because they are 10 times more. They're 10 times less. we don't increase our resistors, we increase our currents. We reduce our resistors by a factor of 10, increase our currents by a factor of 10. So to get smaller, to come to the units there, to the tens there, we would have to do the same. Come here and say that part there, we want to move it and say we want to have that as what? Reduce that by a factor of 10. How do we do that? We come and say, so these two, what do you notice? For every, because our BCD is 4 bits, all right? It's 4 bits, so we need to have 4 sets of resistors for each, all right? Only thing is, within the same unit, within the same column, we are going to have them differing by a factor of 2, okay? But between columns, they are going to differ by factors of hundreds, all right? Sorry, by factors of 10, all right? So it's decimal, so it's going to be factors of 10. So it means here we are going to go 1 over 10 less. Again, it's a factor of 10, only we are going to make our what do we do? The currents, these are the currents. The currents are going to decrease, are going to increase by what? By a factor of 10, but the resistors are going to be increased by that factor, all right? Our resistors are going to be bigger. So if we want to go there, if you wanted to include that minus 3 there, we would have to come in there and say, you cannot be, yes, okay, you cannot be 100K, you cannot be 50, you cannot be 25, you cannot be that, but you are going to be 10 times more. The currents are going to be 10 times less. We are going lower, but the resistors are going to be 10 times more. So this is going to be 10 times this, 1 meg, 10 times that, 500K. Is still having a factor of 2 within itself because this is 2 times that, all right? 10 times 25K is going to be 250K. And again, this is 2 times less than that. And then lastly, it's going to be 125. So we can obviously go higher. If you want to have 100 Hz, we're going to divide by 10 there. The currents, the resistors are going to be 10 times bigger. And if you are going to want hundreds here, you are going to increase the currents by a factor of 10, and then that means the resistors are going to go even smaller, all right? So what does it mean? If we had, for instance, obviously this is connected together, this is connected together. Oh, this is connected together, so this comes and it connects to the other set. Okay, so now, and this one here is connected to that set there. So I don't know whether, of course, would make it a nice and straight column here, but for me, it makes it easy to say these are the what? These are the tens, these are the units, these are the 100 Hz, and you can see these are currents, all right? These are currents. The factors of the currents are going to increase or decrease according to whether you are going what? Bigger or higher. That means, remember, conversely, it means that the resistances are going to, if the currents are going smaller, conversely, it means the resistors are going higher, all right, bigger, all right? So now then you see that this is another set of 4. Why? 4 bits, but you say you want 0, 0, 0, 1, 1. Remember, the smallest resistor gives us the what? The most significant bit. All right. So we come here and we say, all right. So if we were to do this here, it wouldn't be done there. We would have said, to accommodate our tens, we would have said, but we're not done. We have 0, 0, 1, 1. So only what about the ones? That's 5 volts. So that is going to be 5 volts and 500K. That will be plus 5 over 500 kilo. And the other one is going to be what? 5 volts divided by 1 meg, 5 over a meg. And if you bring this into your math here, you will see that that is where our comma 3 is going to come from. Let's see if it gives us 3. Let's be very factual. We only worry about this part. This here is 5 times the k's, remember, fall away. The k falls away. Here this changes to k because a k fell away. All right, so if we multiply now, you're going to see that we need to have 100 divided by 500, and obviously that's 0.5. Let's go 100 divided by, no, not 0.5, 0.2. That will be 0.2. It's 5 divided by 2. Okay, no, it's 2 divided by 5. No, it's 100 divided by 500. It's 1 divided by 5. 100 divided by 500 is 1 divided by 5. So it is what? 0.2. And then there, last but not least, you have 100 divided by 1,000. That's 0.1. And you can already see 120 times 5 is 100 divided by a k, which is 1,000. That's an easy the sum there. It's a factorial, so it's going to be 0.1. Okay, so that there gives you 0.3. There is our little 3 coming in. So as you can see, what have we done with this little circuit? We've converted BCD. It is BCD. BCD means binary coded decimal. So it is still our decimal to analog converter, but it is a specific one where we have BCD, so it will be fed in by what? By BCD encoders. All right, I hope that was easy enough. I hope you had fun. Keep coming back for more. Let us remind you, subscribe, and each time we drop something, you will have a notification to remind you. If you like us, hit the like, and let's meet when we look at, I want to, even though I'm looking at operational amplifiers, and I was looking at what call this? I was looking at the summing amplifier. I have also gone on to show you how the summing amplifier. This is one example. I don't want to make this too long. This is already long enough for me. So this is one example. We're going to come back and show you how we can do this in an alternative way. All right, in a different way. All right, we can still do this analog to digital converter, but in a different way. So then I hope that was nice. Let's meet for the next session. Our next session will be looking, we'll still be looking at our summing amplifier as a digital to analog converter, BCD, specifically BCD to analog, but we'll be doing it in a different way. All right, all we'll be doing is trying to see how else can we do this other than varying the resistors. Is there a different way where we can vary this? I think you should already be thinking about it, but anyway, let's not jump ahead of ourselves. See you when we meet next. Hit that like, hit that subscribe. Cheerio.